It's my pleasure to introduce our speaker today, Dr. Christine Wilson. Dr. Wilson is a distinguished university professor at McMaster University, where she has been on the faculty since 1992. Today, Dr. Wilson will be talking about dense gas and star formation in nearby starburst galaxies. Without further ado, I now turn control to Chris.
All right. So I'm really pleased to be here today to be able to tell you about some of the recent work from our group on dense gas and star formation in nearby starburst galaxies with ALMA. So give you a little introduction. Today I'm going to start off by giving you an overview of a lot of the recent work measuring gas in galaxies, and in particular focusing on the relationship between gas and dense gas as well as star formation. And then I'm going to talk about some of the work we've been doing on primarily nearby starburst galaxies with ALMA, looking at, again, the star formation law and some unusual gas properties in nearby ultraluminous and luminous infrared galaxies, and then drawing on an archival sample from ALMA to look at the properties of dense gas in a sample of 9 nearby galaxies. So I want to start by acknowledging my students in my group. You'll see work from all of them today in my talk. My former postdoc, Toby Brown, who's recently moved to NRC Hertzburg in Victoria, British Columbia. My former students are collaborators around the world, and also the various Canadian funding sources for my research. So when we want to look at the star-forming gas in galaxies, we're trying to look at molecular hydrogen, because this is the phase that forms stars and galaxies in the local universe. Molecular hydrogen in galaxies is typically very cold, 10 to 50 degrees Kelvin, and quite dense, above 100 particles per centimeter cubed. The problem is under those physical conditions, molecular hydrogen is totally invisible, because you need kinetic temperatures of about 200 Kelvin in order to excite the J=2 level by collisional excitations. So when we study molecular gas in galaxies, we're not observing H2, but we're observing carbon monoxide, CO, which is the second most abundant molecule in the interstellar medium. CO is very handy because it's easy to excite the lowest rotational transition collisionally, because it's just 5 Kelvin above ground state. And so carbon monoxide is a good tracer of the total molecular gas content of galaxies. We also, in the era of ALMA and new sensitive receivers on large single dish telescopes like IRAM, look at other fainter molecular lines that allow us to probe different physical conditions in the gas. And in particular in this talk, you'll see a bunch of data for hydrogen cyanide, HCN, which has a higher critical density for excitation than CO, and therefore will trace the denser gas, and is thought to trace the regions where star formation is actually occurring in giant molecular clouds. So if you're someone who studies stars and galaxies, you might wonder, why do we care about the gas? And the reason we care about gas in galaxies is because the gas is the fuel for star formation. And star formation, the presence or lack thereof, drives a lot of the appearance and the properties of galaxies in the universe. So this is an illustration of a seminal work from almost 15 years ago by Rob Kennicott and his collaborators, looking at the relationship between gas and star formation in the nearby spiral galaxy M51. And if you look at the scatter plot on the right, you see the star formation rate plotted versus the gas density. The blue points are when the gas is measured with atomic hydrogen, and you can see that there's almost no correlation between the atomic hydrogen and the star formation rate. The black and the green triangles represent the correlation with the molecular gas, where we do see a good correlation with a power law slope of about 1.4 for this particular analysis. We also see correlations between star formation and lines tracing the denser gas, such as this work from the paper by Uzero et al., comparing star formation rate to dense gas traced by HCN. And again, we see a good correlation going from sub-kiloparsec scales in galaxies at the low surface density end up to global measures of very active galaxies at the high surface density end. Here, the slope is closer to 1, with a possible even going sublinear at the low surface density end. Another way to look at this plot was in a paper by Molly Gallagher, Adam Leroy, and their collaborators in 2018. Here again, you're seeing star formation rate plotted versus dense gas mass, but each of them have been normalized by the total gas mass, so that we now have essentially the star formation rate per unit gas mass versus the dense gas fraction. And again, we see a roughly linear correlation, although with quite a bit of scatter. And in some individual galaxies, these two quantities are quite well correlated, whereas in other ones, they are not. Now, we can also extend these studies up to the very high star formation rate regions of galaxy mergers and the extreme ultraluminous infrared galaxies. This is one plot showing you that relation. Again, now we're looking at star formation rate versus dense gas. The image on the left shows you a far infrared contour plot of the antennae, the closest merger to us, with circles indicating the regions where we've measured HCN and star formation rate using infrared in a paper published last year by my student Ashley Bemis and I. And then on the right, you see the mostly linear correlation between these two properties. One of the things that's interesting in this plot is the points that deviate from the correlation. So hopefully my mouse will show up here. And if it doesn't, there it is. So the nuclei of the merging system, the stars here, are somewhat below the relation, indicating that although they seem to have lots of dense gas, they're rather underwhelming in their star formation rate. And similarly, our own Milky Way, the central molecular zone, shows the same type of properties, bright HCN emission, but relatively less far infrared emission or star formation, given the amount of gas that's there. So in a paper last year, we looked at the correlation between star formation rate and molecular gas mass in a sample of 5 extreme star forming systems. These are all mergers or merger remnants with star formation rates more than 100 times that of our Milky Way. And when we look at the star formation rate versus the molecular gas mass here, we see a strongly nonlinear slope, a slope of about 1.7. And this increase in slope at the high surface density end has been predicted by theoretical models of the equilibrium state of the interstellar medium in work by theorists like Bruce Elmgreen and others. One of the very interesting things about these galaxies is that we can calculate the efficiency per freefall time in these systems. And here we're looking on average values over a few hundred parsecs in each point in this plot. In these galaxies, the efficiency per freefall time is about 5 to 7%. And this is significantly higher than the efficiency that's seen in normal spiral galaxies of about 1% or even a bit lower, and what's typically assumed in computational simulations of star formation in galaxies. So these galaxies with extreme star formation rates are also turning their gas into stars with a much higher efficiency, almost an order of magnitude higher than what you would see in a normal star forming galaxy like our Milky Way or M51. Now, one of the interesting things we're trying to do in our group is to understand why the star formation is getting kicked into overdrive in these extreme starburst systems. And one of the ways we're doing that is trying to look on the scale of individual giant molecular clouds in one of these systems, the nearest luminous infrared galaxy, NGC 3256. And this is only possible because of the high sensitivity and angular resolution that's achievable with ALMA. So this figure from my student's work, Nathan Brunetti, that has recently been submitted to monthly notices, shows you a comparison of the properties of the gas in NGC 3256 compared to a number of spiral galaxies from the FANG sample on ALMA large program. We've looked at a wide variety of physical properties, but I'm highlighting one here, which is the peak brightness temperature of the gas on roughly 100 parsec scales. peak brightness temperature crudely traces the kinetic temperature of the material. And what you can see if you look carefully is that the medium in NGC 3256 is significantly warmer than the medium in the FANGS galaxies. And in the centers of 3256, we're getting up to brightness temperatures of almost 20 Kelvin, much higher than anything seen in the FANGS sample. Another interesting aspect of this brightness temperature is how it changes as you change your angular resolution. In 3256, we see almost no change in the brightness temperature as we go from a resolution of 55 parsecs to a resolution of 120 parsecs. And that's shown in the black here in this plot. But the galaxies from the FANGS sample, aside from the antennae, which is shown in orange, generally show larger changes in the brightness temperature as you go from small to large scales, indicating that the interstellar medium is being resolved structurally into clouds in those galaxies. So what we think may be going on in these very active galaxies is that the molecular gas becomes the pervasive medium of the galaxy. Rather than the space being filled by atomic gas like it is in our Milky Way, it's now being filled by molecular gas. And that may be a critical factor that's causing the much higher star formation rate in these systems. Now, one of the interesting problems in looking at these starburst galaxies is doing a good quantitative conversion from the CO emission that we see to the molecular hydrogen. This is known as the CO to H2 conversion factor. And while it's reasonably well known and reasonably doesn't vary too much when we look at spiral galaxies, when we go to very active systems, we think this conversion factor changes by a factor of 4 or more. But it's rather hard to get a good handle on it. So one of my other students, Hao He, has a paper that's recently been accepted where, among other things, he modeled the CO emission lines in an early stage merger, ARC-240, and found for that galaxy that the CO to H2 conversion factor was very close to the value that we see in ultraluminous infrared galaxies. So even though this galaxy pair from kinematic modeling of H1 data has just been through first passage of the merger process, that close first passage in this particular system has already changed the properties of the interstellar medium. And the two galaxies in this component are quite far apart. They're 20 kiloparsecs apart. So they look more like a pair than a merger, but something quite different is going on in the molecular gas in these galaxies. So one of my focus of my own research over the last 5 years has been looking at CN, cyanide emission from nearby galaxies. And I got interested in cyanide emission because models of photon-dominated regions suggest that CN emission should be produced when you have high-density gas that is exposed to strong levels of far ultraviolet or X-ray radiation. And CN is astrochemically linked to HCN by a photodissociation. And so this leads you to expect a picture where HCN will trace dense gas that is in inner parts of clouds shielded from ultraviolet radiation, while CN maybe traces the outer, more UV exposed regions. And so this gives us a different way to look at the dense gas in galaxies. Serendipitously, the ground state line of CN is only 2 gigahertz away in frequency from the 12CO 1-0 line. And so this means that almost every time someone chooses to observe 12CO 1-0 in a nearby galaxy with ALMA, the dataset also contains CN. And so in a paper I published a couple of years ago, I used the ALMA cycle 0 data to build a sample of about 10 nearby galaxies with both CO and CN detections, and found some interesting and intriguing variations in the strength of CN relative to CO that looked like they correlated with the presence of a starburst or possibly with the presence of an AGN, but it was a little hard to make sense of that. So as a result, I realized we needed to also look at HCN, which gives us a more complete picture of the dense gas. And this led to work on an ALMA archival sample of dense gas in galaxies. So about 3 years ago, I went into the ALMA archive to search for all the galaxies that had been observed in CO, HCN, and CN with ALMA, and that showed some extended emission. And I came up with a sample of 12 galaxies. I eliminated 3 of them for a variety of reasons and was left with a sample of 9. To that sample, we've added the antennae for some of the analysis I'll show you later, but it's not included in the CN analysis because we did not have CN data at the time for that galaxy. So this sample of 9 galaxies varies from an ultraluminous infrared galaxy to nearby spirals, but they commonly have at least a starburst or possibly a Seyfert nucleus in the center. So they're all high intensity systems. So this is an example for one of the galaxies in the samples. Circinus is a nearby spiral galaxy with a Seyfert nucleus. You can see the CO intensity is very nicely extended in the center part of the galaxy. And then if we zoom in, we look at the HCN to CO ratio and we see enhanced HCN emission in the center near where the AGN lives. If we switch to the CN to CO ratio, we also see an enhancement in the center near the AGN. But interestingly, when we look at CN to HCN, the dynamic range of the variation is much, much smaller. And remember, the models predicted that ultraviolet or X-ray emission would enhance CN. And we're not seeing a very strong enhancement despite the presence of a really quite booming Seyfert nucleus in this galaxy. That conclusion that CN and HCN track each other very well extends to the entire sample. So this plot is showing you on a log-log scale, the CN to HCN intensity ratio plotted versus the star formation rate surface density. And you can see that the relationship is really quite flat. Over nearly 2 orders of magnitude in star formation rate surface density, and so presumably increase in ultraviolet radiation surface density, there is no significant trend or change in this ratio. And in fact, the individual values of this line ratio scatter by only a factor of 10, and the mean values of the individual galaxies only range over a factor of 4. So we really have a very constant ratio across this sample of galaxies. This is what one of the more detailed PDR models showed for CN and HCN from Boger and Sternberg in 2005. And with a couple of different assumptions for how you allow ultraviolet intensity to vary relative to density, you can see from the plot that we would expect variations in this line ratio as we vary the ultraviolet intensity. And if we just compare that to the previous figure, you can see that particularly relative to the blue curve, which is their more fiducial model, we are not seeing the same upturn in the ratio of CN relative to HCN that would be predicted by the models. Now, these models assume a constant density cloud, and we know molecular clouds are in fact very clumpy. So my suspicion is that it's the clumpiness of those clouds that's allowing the ultraviolet radiation to make its way deeper into the cloud and thereby exciting widespread CN emission. And unfortunately, nitrogen astrochemistry is rather complicated. And so while I would like to see a clumpy PDR models, including nitrogen chemistry, so we could look at CN, I'm not sure they're going to appear anytime very soon. Just to look a little more detail at a few of those galaxies, my student Blake Ledger is working on 3 of the galaxies from that sample. And we've plotted them here, not the ratio, but now just CN relative to HCN. And plotted this way, we see that there are some subtle variations in the relative strength of CN compared to HCN in these galaxies. And so it may be that we will be able to see excitation effects due to AGN or central starburst when we look more closely. For these 3 galaxies, we have not just the ground state line, but also 2 additional higher excitation lines for each molecule. And so we will be able to do a radiative transfer analysis and find out whether differences in the lines that we see are due to differing excitation or possibly more likely different actual abundance ratios. Ashley Bemis is also working with the data from this sample for her PhD thesis. And one of the things that she's doing is looking not just at the HCN data, but also HCO+, which is also sometimes used as a tracer of the dense gas. And she's been comparing them with theoretical models using probability distribution functions for the density, allowing the Mach number to vary, allow the kinetic temperature to vary. The models are shown as the black lines in these figures, and the colored points show the individual measurements for the galaxies in our sample. And one of the things that we think is needed to match the models to the lines are abundance variations, as well as probably changes in the external pressure that the gas is feeling. So this is a sample of 9 galaxies, which is certainly much better than 1. And the fact that they're resolved means we have many individual points. But in studying molecular gas in galaxies, the challenge is always to get to large samples because it is time consuming to collect the CO data for nearby galaxies. So my student Ryan Choen had recently submitted a paper where he has been looking at the correlation of the 12 micron emission relative to CO emission on kiloparsec scales using the Edge Khalifa sample for the CO and WISE for the 12 micron. And one of the things that he's found is that the 12 micron surface brightness alone is a very good predictor of the CO surface brightness and therefore the molecular gas surface brightness in the spiral galaxies in the Edge Khalifa sample. And it's an even better predictor of CO than resolved optical quantities like metallicity or visual extinction. And so I think this is a very interesting new result that may allow us to produce much more expanded samples of molecular gas using 12 microns as the tracer rather than CO, because of course we have the WISE all-sky survey to work with at 12 microns. Finally, I just want to highlight one of the new large programs with ALMA. This is led by my former postdoc, Toby Brown, and this is Vertico, the Virgo environment traced in CO, where we are mapping a total of 51 spiral galaxies in Virgo to try to understand what the environmental influences are of being in a dense cluster environment on the molecular gas and star formation. One of the advantages of looking at Virgo is that it has been extremely well studied in almost every other wavelength you can think of, from ultraviolet to optical to near infrared to 21 centimeter. And so there is excellent multi-wavelength data with which to compare. The one thing that was missing was the high resolution CO data, and we now have that with Vertico. So we expect the public data release early in 2022. The survey was almost complete when ALMA had to shut down in March. And if you have a scientific project and you're interested in access to data before then, please get in touch with either Toby or me or one of the other people in the survey. So with that, I will just put up my summary slide. I'm saying ALMA is a fantastic tool for revealing molecular complexity in nearby starburst galaxies. And the ALMA archive is just a fantastic resource for being able to build large samples and answer new questions beyond what the original target of the PI who wrote the proposal was. So thank you very much.
Thanks, Chris. We have a few questions. If you have some time to take them, maybe take a drink of water.
Yeah.
One of our questions was right from the very beginning when you showed a slide that had in the denominator a total gas mass. So the question is, how do we separate the dense gas from the total gas?
So the way that in the extragalactic community we typically separate them is by the molecular tracer we observe. So CO, because it's excited at a wide range of densities, we think traces almost all the molecular hydrogen galaxies, even the lower volume density material that isn't forming stars. And then HCN seems to need higher densities to be excited, and so is better at tracing the denser star-forming glass. So typically when we talk about dense gas versus total gas, we're comparing some high-density tracer, HCN, possibly CN in the future, to CO.
And is there some characteristic density that might distinguish the two regimes?
That's actually a really interesting question. The critical density, where collisions can keep up with radiative de-excitation, for HCN is actually about 10 to the 6th, but particles per cubic centimeter. But more recent modeling work and observations suggest that HCN actually will trace gas down to quite a bit lower densities, down to maybe 10 to the 4 or so. Whereas the similar argument for CO is down to about 100 particles per centimeter cube.
Okay, perfect, thank you. One of the participants noted that M83 seems to be different than the rest of the objects we're looking at in terms of CN. Seems systematically low, regardless of local star formation and local star formation surface density. Do you have a reason for that?
Yeah, well, that's very well spotted. I get asked that question every time I show this plot. So M83, actually, my gut reaction is that it may be something about the data in M83. M83 was observed in ALMA cycle 0. That's where these data are from. And it was a challenging large area mosaic. So M83 is actually the only galaxy in our sample where the CN emission is what's limiting the pixels we can include in the plot. For all the other galaxies, the limiting factor is actually the 93 gigahertz radio continuum, which is where this talk, which is very ALMA focused, actually links to the NGVLA, because we would be able to get much better radio continuum images to trace star formation in these high excitation galaxies. So my guess is part of what's going on is a systematic effect in the data. It is also a one of our higher resolution targets, and so there, if I look at the actual intrinsic resolution, there are offsets between the CN and the HCN a little bit, which I haven't really explored. So it could be a real difference, but my first answer is it's probably due to sensitivity limitations of the CN data.
Okay, here's a good general question. It's asking about the efficiency of star formation in spiral galaxies. Could their efficiencies be explained by the turbulence and the the velocity structure in spiral disks?
So I guess so the extragalactic community uses two different definitions for efficiency. So the efficiency per freefall time is the one that I showed, and that is a more sort of more physically based efficiency. Historically, we've also used just star formation rate divided by molecular gas, which is not an efficiency, it's 1 over time. So we flip it and call it gas depletion time. That's not really answering your question though. I don't know what causes the star formation efficiency, sets it in spiral disks. I do think that this is really one of the long-standing problems in the field, and there are, I think, I'm trying to think of it, Diedrich Kreuzen or Mark Krumholtz or others have kind of characterized this as you either have, I'm going to get this wrong, you have either galaxies are very slow at forming stars but very efficient in the end, or they're very fast at forming stars but very inefficient, right? And they have the pairs wrong, but you kind of hopefully get the sense of that. So I think why galaxies don't form more of the gas into stars more quickly, which is the underlying efficiency problem, I think it's still not really completely understood.
Well, here's a maybe even tougher general follow-up question to that. Do we have evidence for Seifert nuclei impacting that efficiency?
Ah, I don't know that we have evidence for or against that.
Yeah.
Short answer.
Yeah, I told you it was a hard one. A few more here. For galaxies where it seems the molecular gas is pervasive throughout the disk, are there resolved H1 data? The idea here is there H1 throughout the disk too, just at a lower level?
Yeah, that's a really good question. I think it's hard to answer though. So we, with the ALMA data, we have gone down to sub-arc second resolution to get to the 50 parsec scale in NGC 3256. You can't at the moment get to sub-arc second resolution in atomic hydrogen. So again, maybe that may be another challenge for the NGVLA. That if you really wanted to see, is the H1 there and how much of it is there, you'd need NGVLA for that high resolution and sensitivity. But in spiral galaxies, the H1 seems to be almost always there at a surface density of about 10 solar masses per parsec squared. I would not be at all surprised if the same is true in these galaxies, but the H2 is at 1,000 to 10,000 solar masses per parsec squared. So the H1 would be just 1% or less per unit area.
So are there, just to follow up on that, are there other issues right at the tip of your mind where you would think NGVLA would bring some interesting results to the table here?
Oh, well, I mean, NGVLA, if it can get up towards the COJ = 1 to 0 line, you would be able to do these types of studies faster and with even higher angular resolution. You'd be able to get some of the galaxies in the northern hemisphere as well, which sounds like well, what's the big deal? But there are some really interesting galaxies that people would like to look at that are too far north for ALMA. So
yeah. Are there any molecular lines for H2 in the radio that might be used as absorption lines for absorption line probes for AGN backlights with more sensitive facilities like the NGVLA?
Yeah, so H2 molecular hydrogen, no, I don't think so. The longest wavelength line of molecular hydrogen is at about 28 microns in the mid-infrared. That's the J = 2 to J = 0 rotational transition. Everything else is at shorter wavelengths.
Yeah, I think the questioner sort of maybe anticipated that answer and so asked also, are there other ways to sort out issues related to CO-H2 variations?
Well, there are, and this is something that my students and I have been working on, have been talking about. I mean, there are a variety of different ways to approach it. One of the things you can do is if you can get down to cloud scale, and if the clouds are gravitationally bound, then the gravitational mass gives you an independent measure of the mass you can compare to the CO brightness. That was one of the original goals for the 3256 program. I'm not sure that we'll be able to do it because if it doesn't break down into clouds, we can't use that technique until we get higher resolution. Another way to do it is to compare measurements of the dust, because you can fit for the dust mass and assume a gas to dust ratio and compare that to CO. Linda Tacconi has done a lot of work on this at higher redshift galaxies, and I think she's talking later on in the summer in the series. Another thing that people have tried is atomic carbon, which is a little bit more of a simple, it only produces 2 emission lines in the radio, so that makes excitation and things simpler. Loretta Dunn gave a very nice talk at the ALMA meeting last October in Sardinia, comparing CO and dust and atomic carbon lines. I believe it was for some galaxies from the H-Atlas sample. So no one technique, every technique has its assumptions, but many of the assumptions are quite independent. And so I think by trying to come at it from multiple different directions, we should be able to zero in on this problem. One of the limits in these nearby merging galaxies and the conversion factor is that we do have dynamical mass estimates in the center from the motions of the gas. If you used a Milky Way conversion factor in some of these galaxies, your molecular gas mass would exceed your total dynamical mass. And so that at some level sets a real hard upper limit to the conversion.
You still good? Got energy? More questions?
Sure.
Awesome. You showed a comparison between 3256 and some FANG's normal star-forming galaxies.
Yep.
Do you think the spatial filling factor is able to explain the difference in peak temperature?
No, I don't think so. I mean, the FANG's data are also very high resolution. So the FANG's data, I'm actually not sure if the plot I was showing you was at the 50 parsecs or the 120 parsec resolution, but either way, FANG's is getting down to giant molecular cloud scales, where you would expect the molecular gas to be pretty close to filling the beam, the synthesized beam. So no, I think there's probably actually a difference in the physical properties. The kinetic temperatures are probably higher in 3256 than in the FANG's.
Okay. Do you know what the CN to HCN ratio is for the CMZ?
Really good question. No, I don't. If someone's done a molecular line survey of the CMZ, then they probably have the data. Sometimes when you do galactic molecular line surveys, though, people stop at 13 CO because they know 12 CO is so optically thick it's not going to be that useful. So lots of people have been studying the CMZ, so probably someone has it for some of them. I wonder if there's this cloud called the Brick that was studied a lot in the early days of ALMA, and I remember they had multiple molecular lines, but again, I can't remember if they went up to 12 CO.
This is related to a question I was thinking of listening to your presentation. So it's a question on the clumpy PDR modeling. Can you explain on possible ways forward to do this? And then they follow up by saying it would be very relevant to irradiation that we're seeing in class 0 protostellar outflow cavities traced by C3H2 and CCH, different spatial scales and densities from galaxies, obviously, but anything to get a feel for how deep UV and X-ray photons can get into clumpy galaxy protostar media.
Mm-hmm. Yeah, so I think the clumpy problem, the clumpiness of the simulations is not really the problem. I remember there was a paper by Stella Offner and also maybe papers by Simon Glover where they had a real hydrodynamic simulation of a molecular cloud where they could see clumps, but they also tracked the chemistry and the star formation and so on. And those models were able to solve a long-standing problem with atomic carbon. So a slab PDR model will predict very wrong things for the atomic carbon, and that's been known since the first atomic carbon measures in the 80s by people like Jocelyn Keane. That atomic carbon was much more widespread. And so the idea is you have UV coming in from one side, and if you've got clumps, it can make it through past clumps and hit the front edge of a deeper clump, and you find C1 through all of it. So I wouldn't be surprised if the same thing worked for CN. I think the difficulty, my understanding of the difficulty from talking to Simon Glover is that the nitrogen networks are just complicated. And so to implement your nitrogen astrochemical network in one of those simulations is much more difficult than just having the carbon and oxygen, which is what you need for CO and C and other interesting molecules. So I think the difficulty is in the nitrogen astrochemical network. I think it could be done. The question would be whether it would be right. And so people, you know, the experts might want to do it when they realize there were all these uncertainties in the network.
Oh, another good general question is why is it difficult to detect CO versus those dense gas tracers?
Well, so it's more difficult to, so CO is easy and the dense gas tracers are hard. So if I said that the other way around,
Okay.
I apologize. The main reason is just the brightness of the lines. So CO is the brightest molecular line you'll see in a galaxy, in, you know, say around 3 millimeters, just say, pick a wavelength range. HCN and CN are typically a factor of 10 to 30 times fainter. So to get the same signal to noise, you need 100 to 30 squared times the integration time. Yeah.
Okay. Oh, this person might follow up offline with you. They want to know what cycles you used for your archival data.
Okay, so
on CN.
yeah, so I believe the archival data is mostly cycles 0 through 3. I did the search in 2017 and it was all publicly available data. And so it's just, you know, whatever would have been public in August 2017.
Okay.
We've gone back and looked and found some more galaxies and started processing them, but they haven't been finished and folded into this analysis.
Well, let's finish up with just one more question, Chris. It's, is the CN to HCN ratio, is that affected only by photons, or could high energy particles also drive it?
So high energy particles like cosmic rays, I don't know. I don't really know how cosmic rays change the chemistry. So if cosmic rays affected things like the ionized carbon or the atomic carbon, then probably that could affect CN, because that's one of the formation mechanisms is linked to ionized carbon interacting with a nitrogen molecule. But I don't know that anyone's done that modeling. Models that have the CN in them are not that common.
Mm-hmm. Okay, well, thank you so much for the presentation and being a good sport and answering all these good questions.
Thank you. Thanks everybody for listening.